ません。
Argument though for the some of the natural numbers being countable, like you just keep adding numbers to the end forever. So for one, first number is actually 1, second digit for instance is 3, and then for 3 the second digit out is a digit you add a number, and so on forever. So you have an infinitely long number. You know it's still the set of natural numbers, but by using that argument, you can argue that the set of natural numbers is not countable.
You know, someone who argued that ACM was decidable. Listen, it's good thinking. That's true for a while too. But now you're arguing that the same argument that's used here we can use to prove that the natural numbers are in fact not countable. Because we already know that they are. Yeah, so we'll talk about that out in a minute and see where that seems to go wrong. Okay, this is a good thought. I appreciate that. Let me just first finish with this and then make sure everybody understands what this is doing. And then we'll see what seems to be the problem with the natural numbers. Okay, so anyways, everybody get this? How this works? That we suppose that there's a one-to-one correspondence between the naturals and the reals, which means there has to be a table like this. Okay, but if there is a table like this, we construct another real number x by the diagonalization idea. This is where the diagonalization comes in. We're diagonalizing. It's the ith number or the ith row in the table and the ith digit here after the decimal place. And so we're going down the diagonal and we're changing the value, setting the digit in x to be different than the digit in what we're seeing here. For technical reasons, I'm going to avoid 0, 1, and 9. And that's just because 1.99999 is equal to 2. This goes forever. Kind of annoying. But the point is that suppose you had 2 in the table, and well, actually, this is changing things. This is equal to 1. Okay. Suppose you had 1 on the table, and you changed it to make x equal to that. Okay, these are actually the same number if you believe in infinity and mathematics and all that stuff. So just to avoid any of those kinds of degeneracies, I'll just not use 9. I think I'm worried that we could get into similar problems with 0. Okay, anyway. But back to the main point. The main point is now I create this number x, which is not in that table, and therefore this correspondence is not what I want to run to, and that means that the real numbers are not countable. That's how that proof goes. Okay. Well, I guess I'm thinking. All right, I'm going to decide the picture, but okay. So I'm trying to answer the question. I can see that we're not actually going to get to this today, but I'm going to show you proof of this. The ACM is not decidable by using a diagonalization idea. So all of this what we're doing today is preparation for that proof. But let's look back at the naturals and see if we can get out of this trap. So question. Can't we use this to show that the naturals, that n is not countable? And I think what you had in mind was, well, here are the naturals that we want to do the correspondence with. And then there's some way we're going to do a one-to-one correspondence. And it doesn't have to be the most natural one of 1 corresponding 1, 2 corresponding 2, and so on. But there's going to be some natural number that's written here. 3, 4, 5, 6, 7, 8. It's 1, 1. Okay. And then there's going to be some natural number that's written here. 36, 40, 485, 907, 95616, 753, 860, whatever. It's numerating phone numbers. Okay, so you want to run it onto, and then you want to do the diagonalization. You want to create a new integer, I, create I, integer I, that is not in the table. Okay, so we'll do the diagonalization. The first digit of I should be something different than 3, right? So what do you want to make it? 7? Okay, so 7, I equals 7. And the next one should be something that's not 6. Okay, so, lucky 7. I'm going to just shorten this a little bit. And the next one should be something that's not 5, right? And what do you want to make it? Like 7, 2, okay. And the next one, look at the fourth, it's the fourth entry, we look at the fourth digit, but oops, there's no fourth digit. Okay, yeah.
I don't think every ordering has to be as a correspondence.
No, not every ordering. This is
Ordering exists, or there's no ordering.
Yeah. Like I said, suppose this is a correspondence, okay? For the natural numbers to be countable, I mean, we already know they are by definition, but there should be some correspondence between the natural numbers and the natural themselves, okay? And I'm just saying, suppose this is one. Then we'll do this diagonalization. I could have looked at 1 with 1 and 2 with 2 and tried diagonalization there, and we'd see even sooner what the problem is. Yeah.
You want to actually go the other way, like moving away from the greatest point, like going to the left, so that you start at like, up to 1 spot, and then 10 spots, and then 1 spot, and then like that. From here back here.
Okay, so let's see first what's happening with scaling here. So what's failing here is we try this diagonalization, and we get to a point where there's no digit in the required position. Yeah.
Well, there's no digit, then couldn't you just put any digit? And as long as there is a digit in that place, then you know it's just a difference, because that has nothing there. And if there's something there, it's a different number.
Okay, so now I'll
just add anything there.
Okay, just add anything there, yeah, like an 8. Okay, and since this number doesn't have a fourth digit, and this number does have a fourth digit, this one will not be equal to that one.
Yes.
Okay, yeah.
I would be in numbers.
Because what? Okay, so here's another problem, is this is going to go forever. All right, so how long is I? I is infinite. Now, real numbers are permitted to be infinite. A real number can have an infinite number of digits after the decimal point, but no natural number. Every natural number has a specific finite size. The set of natural numbers, there's no bound on how big those numbers are. They have numbers of size 5 digits and 25 digits, and there's no bound on them, but any particular one just has some fixed number. But here, with this diagonalization, what you're trying to do, you'll end up creating something that looks like it has an infinite number of digits. So I think we got out of that hole. Now, the other suggestion was to put a lot of zeros, an infinite number of zeros, on the left side of our integers, okay? And it's not clear to me exactly what that means, but even if you did that, when you end up diagonalizing, you still have the same problem of creating a number that has an infinite number of digits, and so it's not in it's not the naturals. Okay, so this is diagonalization. This is Cantor's proof that the real numbers are not countable, and therefore they're a different infinity, a bigger infinity than the naturals. Okay, if you can conceive of what it means to be a bigger infinity. But anyway, technically, it means that they're not countable. Okay, they're uncountable. And next time we'll use this diagonalization idea to get back to the question about ATM and show that ATM is undecidable. Okay, and this diagonalization, I find that a much simpler way of doing these undecidability proofs than the self-reference. Okay. So last time we were talking about undecidability, and the previous lecture I did the proof that certain languages are undecidable, and last time I started talking about diagonalization, and I thought I was going to show you another proof using diagonalization that there are undecidable languages, and in particular ATM is undecidable, and so that's what I want to do starting today. So the reason why what ATM is a set of languages is a language where the input looks like this. This is a description of the Turing machine, and this is some input to that Turing machine, such that M accepts W. Okay, so there's a perfectly good description of the language. It's a set of strings. It's a set of strings that has some particular property. I guess we make this more explicit. M is a Turing machine. static such W. Okay, and we've already proven that this is undecidable. There's no other Turing machine. There's no Turing machine that can take in a description of, that can take in this and decide whether or not M accepts W. Okay? And we did that by self-reference. And you should really, I personally think that's kind of a mind-twisting kind of puzzle sort of proof. And you need to go through it line by line and not that many lines, to convince yourself that that's right, and then try to close your eyes and put it all together in one big picture. And this is the crux of undecidability and non-computability, and the fact that they're and Gödel's proof, and there's a whole big book I'll bring this someday called Gödel, Escher, and Bach. It's all about this kind of self-reference and so on. So it's anyway, it's an interesting idea to get straight. Okay, but today I'm going to show you a different way of proving that ATM is undecidable. By diagonalization. Okay, the first thing to establish is that the set of Turing machines is countable. Well, last time we talked about what countable means. Countable means that set, the set of objects, in this case, set of Turing machines, can be put in one-to-one correspondence with the natural numbers. So, i.e., there is a one-to-one onto correspondence between the Turing machines, the set of Turing machines, the elements of the set of Turing machines, and the natural numbers, M. And we have an idea how you exhibit this correspondence? No. Well, every Turing machine, of course, what I'm about to say has been something we've said and used many times. Every Turing machine, any particular Turing machine, is described by a string over some particular alphabet. In fact, we can fix a finite alphabet once and for all that can describe all the different Turing machines. Okay, so each Turing machine is described, or can be described, by a string in some fixed alphabet. We talked about this when we were looking at universal Turing machines and how you code a Turing machine on input tape for the universal Turing machine. Basically binary alphabet plus some punctuation marks to separate the transition functions, and but that's not it. I mean, you can see the idea that there's a finite alphabet, finite size alphabet, that would work to describe the entire set of Turing machines, of all possible Turing machines. And it's not even that big. I mean, binary doesn't seem like it's going to be big enough. Actually, binary doesn't work. It's just internal numbers of binary, and then 10 to the simple zero, for example, as the punctuation mark. But that doesn't really matter. Whether you have ASCII 256 characters, whatever, that's really sufficient. Okay, this is a important technical point. All right, so each Turing machine is described by some string. All right, so if you have a fixed alphabet, how many, let's say it has 256 characters in it, how many strings of length 1 can there be? 256, and how many strings of length 2 can there be? Yeah, 256 squared. So how many strings of length k can there be? 256 to the k. So for every length, there's a finite number of strings that are possible. So for every length k, there are only, aside from the alphabet base of the k, strings of that length. Okay. Now some of those strings describe a Turing machine, and most of them don't. Okay. But certainly within these strings, if there's a Turing machine that can be described in k symbols, it's going to be within the set of strings. Okay. So certainly any Turing machine that can be described with k symbols, or in a string of length k, from sigma, to be in the sigma of the k strings. Okay. Now, is there a one-to-one correspondence between the set of all strings over this alphabet and the natural numbers? One-to-one onto the correspondence? Yeah, you have all the strings of length 1, followed by all the strings of length 2, followed by all the strings of length 3, and so on. And for any length k, that will eventually be in the list at some finite distance from the start. None of these sets, for no k, is this set infinite. These are all finite. So I can list all strings of length 1, followed by all strings of length 2, those ones, 3, more of them, and then, as you go down, all strings of length K, 36K. And my point again is that this list here is going to be finite for any particular K. So I can now put these strings in correspondence with the actual numbers by just saying string 1, 2, 3, 4, 5, 6, 7, however many this happens to be. Let's say 256. Oh, that was the 256 squared if we're talking about the ASCII alphabet or whatever. And then the next one is 256 squared plus 1, and so on.